Okay, so I'm going to record lecture 9, and we will wrap up SVM, support vector machine. So in today's lecture, I'm going to talk about the general case, the so-called non-separable case. And in this process, actually, we are going to review what we have studied about SVM, but hopefully from a higher level so that we can see the main theme and different components and the global picture more clearly. So therefore, this lecture is half new and also half review in order to consolidate our understanding for SVM. So recall that in the past 2 lectures, we studied the situation where the data are separable. So those are the negative examples, those are the positive examples. And so for those examples on the safety boundary for positive 1 and negative 1, we have the linear logic score. So Wxi plus B for the positive support vectors. So this equal to positive 1. And, excuse me. And for those xi that are negative support vectors, Wxi plus B equals negative 1. Okay. And of course, for all the positive examples, the scores are greater than or equal to positive 1. And for all the negative examples, the scores are less than or equal to negative 1. Okay. And for the positive examples, yi equal to positive 1. For the negative examples, yi equal to negative 1. Okay. And this is a separable case. Okay. And we also know that this margin, or the half for this whole range, so this is 1 over the L2 norm for W, or the length of W. And then in our primal problem, we want to minimize 1/2 for the squared length of W, which amounts to maximizing this margin under the constraints that yi times the logic score is always bigger than or equal to 1, where the score is Wxi plus B. So this is always bigger than or equal to 1 for I from 1 to n. So that's a separable case. But in general, the data may not be separable. For example, we may have a positive example here, so that it goes beyond the safety boundary of positive 1. And we may have a negative example here, also go beyond the safety boundary of negative 1. And we may even have a positive example here, go beyond the true boundary of classification, where the logic score is 0. Okay. And we may also have a negative example here, also going beyond the true boundary for classification. So for this example and this example, they just go beyond the safety boundaries, but they are not going beyond the true classification boundary. But for this example and this example, they actually go beyond the true boundary. So which means these are the misclassifications. Okay, so those are the examples where we cannot account for by this constraint or this separable case. And then we may introduce the so-called slackness variable psi I. So for example, for this example, psi I is how much it goes beyond the safety boundary. And this may be like a 0.6, right? It go beyond safety boundary. But for this example, it go much beyond the safety boundary. In fact, it even go beyond the true classification boundary. This may be like a 1.2. So this psi I, the slackness, is how much you need to relax for those examples, or how much they go beyond the safety boundaries. And this psi I is always non-negative. Okay. And for those examples, so we actually want our classifier to continue to have a very big margin. So we still minimize this 1/2 of the square length of W, the same as a separable case. But then we also allow the slackness, or we allow the violations for the safety boundaries. But we want the violation to be as small as possible. So we also want to minimize, in addition to this 1/2 of a square length of W, a C, which is a tuning constant, times the summation of psi I. So hopefully most of the psi I equal to 0, only with a few exceptions. And then we need to pay a penalty or a fine or a price. That is like how much money you need to pay for each violation. And then you want to pay as little as possible. Okay, so now the primal problem becomes we want to minimize this 1/2 of the squared length plus a constant C times the summation psi I, subject to this yi times this linear logic score to be bigger than or equal to 1 minus psi I. Okay, so that is we allow this psi I so that as long as those example, this example is beyond this point instead of positive 1. So this yi times the linear logic score to be bigger than 1 minus this guy. Okay, so this may be 0.6. As long as it is bigger than 0.4, then that's okay. Okay, so that's a slackness which that we allow for this example, but we also pay a price, how much that we slack. So it's like you pay a penalty, you pay a fine, or how much money you have to pay in order to buy such slackness. Okay, and this psi I is always bigger than or equal to 0. Hopefully, for most of the examples, this number equal to 0, meaning that those examples, they stay safely behind the safety boundary, positive 1 or negative 1 for those examples, but only for those green colored examples, which are exceptions, that you need to pay a price, psi I, as the amount of slackness. Okay, so that's the more general version of the primal problem for the non-separable case, where we introduce the non-negative slack variables. Okay, and then if you look at this problem, now we have W and B as our primal parameters, but we also have psi I as our primal parameters. Okay, and then we have now two sets of constraints. One is that this yi times this linear logic score, you can call this as individual margin. This is bigger than or equal to 1 minus psi I, and this is for I from 1 to n. So this is one side of constraints. And then we have another set of constraint, psi I is bigger than or equal to 0, again for I from 1 to n. So we have 2n constraints. And if we want to apply the Lagrangian type of scheme, then we know that for each constraint, we should have a Lagrangian multiplier. So we rewrite this constraint as something less than or equal to 0. And this gives us a Lagrange multiplier alpha I bigger than or equal to 0. And then for this constraint, for each of these constraints, we also have another Lagrange multiplier and mu I, which is again bigger than or equal to 0. Okay. So therefore, we have two sets of Lagrange multipliers. And recall that our scheme is like this, summarized by this line. So we have the primal problem, which is here, which is constraint optimization problem. And we first write this as a min-max of the Lagrangian, where we move the constraints into this objective function in the form of Lagrange multiplier, which is bigger than or equal to 0, multiplied by a function that is less than or equal to 0, according to this constraint. Okay, and that will be the Lagrangian. And then our next step is to switch the order of min-max to max-min, so that we minimize this Lagrangian with respect to the primal parameters w, b, and psi. So psi consists of all those psi I bigger than or equal to 0 for I from 1 to n. And then we can solve this minimization problem in closed form, so that the minimum is q. For each alpha and mu, we find the minimum of this Lagrangian over wb and psi, so we get this q. And we will see that this q is a function of only alpha. It doesn't involve mu. So we have two sets of dual parameters, alpha and mu, but the q only depends on alpha. And we will see that this is still the same q alpha in the previous lecture. Okay, and we saw this in closed form so that we just maximize this q alpha over this alpha and also mu. So there's some constraints that, as we will see later on, simpler constraint. And this is a dual problem. The dual problem is maximize this dual function q alpha over alpha. Okay, and this problem can be solved very easily. So that's the whole purpose of translating the primal problem into a dual problem. And again, just to clarify, we now have primal parameters w, which is a p-dimensional vector of coefficients, and b, a scalar bias term or intercept term, and the psi, which is n-dimensional vector, consists of psi I, the slackness, which is non-negative. And then the two sets of constraints introduce the dual parameters alpha and mu. Alpha consists of all those alpha I bigger than or equal to 0, and mu consists of those mu I bigger than or equal to 0. So those are also called Lagrange multipliers. And then our Lagrangian, which is a function of both the primal parameters and the dual parameters, consists of this primal objective, and then plus the Lagrange multiplier alpha I multiplied by a function derived from here that is less than or equal to 0. So it will be 1 minus psi I minus yi times this linear score. Okay, so this is less than or equal to 0 according to this constraint. So this function alpha I, which is bigger than or equal to 0, must multiply a function that is less than or equal to 0 according to this constraint. Okay, or in other words, we can rewrite this constraint as this function less than or equal to 0 in the original primal problem. And for that one, we have mu I, which is bigger than equal to 0, multiplied by a function that is less than or equal to 0 according to this constraint, so that we rewrite this constraint as negative psi I less than or equal to 0. Okay, so that's a form of Lagrangian. It consists of the primal objective function plus the Lagrange multiplier times the function that should be less than or equal to 0 in the original primal problem as a constraint. Okay, and after we write in this form, basically we free the constraints so that we solve a unconstrained problem, the min-max problem for this Lagrangian. And this Lagrangian is still concave, convex. it is concave in the dual parameters and convex in the original parameters. Okay, so that's this Lagrangian, and then we can go through this scheme on this at this line in order to solve this problem. Okay, so now let's continue. We go to the next page. Okay, and this give us, let me see if we get to the end. I think do we get to the end? I think we get to the end here. Okay, and then let's see. Yes, we have this Lagrangian. Remember that after we switch min max to max min, we want to solve the minimization of this Lagrangian in closed form. And this Lagrangian is still concave convex function as we showed before. So basically we want to find the saddle point, right? And we solve this minimization problem first. That is for each dual parameters alpha and mu, we want to solve this minimization problem over the primal parameters. Okay. And the minimum of this L function, this Lagrangian, will give us Q alpha, which is a function for the dual variables. And we can easily find the minimization by setting the derivatives with respect to W, B, and psi I equal to 0. Here, psi I for I from 1 to n. And then if we set partial Lagrangian over partial W equal to 0, we get the so-called representer W hat, which is equal to summation I from 1 to n, alpha I, yi, xi. This xi is a p-dimensional vector. Okay, and this is the same for all the 3 rounds for our treatment of SVM. In the first round, we assume b equal to 0 and the data separable. In the second round, we continue to assume the data separable, but b is not equal to 0. We also want to learn b. And in this round, the third round, we assume the data not separable so that we introduce slackness variables psi I. Okay, but we get the same representer. And this result is quite important for us to play out the kernel trick, or for us to kernelize SVM, as we will see later. And then the derivative of Lagrangian with respect to b equal to 0 lead to this constraint, which is a single constraint, alpha I, yi, their summation equal to 0, which means for the positive examples, the sum of alpha I is the same as the sum of alpha I for the negative examples, because yi can only be positive 1 or negative 1. So this is a constraint caused by b. And then if we take a derivative of Lagrangian with respect to psi I and set the derivative to 0, we get this alpha I equal to c minus mu I. And clearly that means alpha I must be less than or equal to c, because mu I is bigger than or equal to 0. Okay, so this actual constraint on alpha I, in addition to alpha I to be bigger than or equal to 0, this is caused by this non-separable situation where we introduce the slackness variable psi I. Okay, and in the end, after you find the W and you plug in this W hat into this L, and with all those equal to 0 and this equal to this one, you will see that the Q alpha is still summation alpha I minus 1/2 of the squared length of summation alpha I, yi, xi. Okay, and this Q alpha is the same for all 3 rounds, including b equal to 0, b not equal to 0, and the non-separable situation. So we always have the same Q alpha. And actually, in the previous lectures, we also derive these three results without taking derivative. For this one, we can actually write the Lagrangian in the form of 1/2 of the square distance between W and this guy. Okay, we write things in the form of a squared distance or squared difference, and then we get this so-called representer result. Okay, and for this one, we actually argue that if this not equal to 0, we can make the minimum to be negative infinity so that it cannot be the solution of a maximum. And similarly, we can use the same argument for this result, that is alpha I plus mu I minus C must equal to 0. Otherwise, we can also let the minimum go to negative infinity so that it cannot be the solution to the maximum problem, max over the dual parameters. Okay, so that is we have different ways of deriving these three equations. Okay, and actually, in this writing this in terms of the square distance, 1/2 of the square distance, and then the rest will be just Q alpha in this Lagrangian. After we realize this equal to 0, and alpha I plus mu I minus C also equal to 0, and then we get the same Q alpha, which is same for all the three rounds. Okay, and then we recall that we can kernelize this SVM. So starting from this representer, and then let f of x be the logit score of a query x, either a training example or more likely a testing example, but any generic example x, we compute f of x to be the score of this x, how we score this x. And then based on whether the logit score is bigger than 0 or not, we classify this example to be positive or negative. That is, y is predicted to be the sign for f of x. And f of x is how we are going to score this x. So it is, it will be this w hat, where w hat is computed from here, w hat times x plus b. And according to this representer result, so that will be summation I from 1 to n, alpha I, yi, xi, and then inner product with x. So we can move this alpha I, yi out because they are just scalars. And then we have xi, x. Okay, and then plus b. So this is how we score this x, so that we can make classification. And then we can also write this q alpha, just as we did before, summation alpha I minus 1/2. So we can write this. We can write this as inner product between summation I from 1 to n alpha I y xi, and then summation j from 1 to n alpha j yj xj, which is the same, and then inner product. And if we write out the inner product, we get n squared terms. So for each pair ij from 1 to n, we have alpha I, alpha j, yi, yj, and then xi, xj, the inner product. Okay, so the kernel trick is that instead of classifying the examples in the original space, we choose to classify the examples in the feature space, phi x. For example, if x is two-dimensional, and we have some positive here, some negative here, and clearly we cannot classify them linearly, find a linear separator, right? Separating hyperplane, that's impossible. But if we go to a four-dimensional space, here I can only draw on this two-dimensional page. So we have x and x1 squared, and x2 squared. Then the data are separable linearly. Actually, you can write this as circle, right? Circle involve this x2 squared, x1 squared. So that's why they can you can separate them. And then we can separate them so that this this separating hyperplane is w phi x plus b equal to 0. So this, if you look at this, on this linear space, this feature space, this boundary is just separating hyperplane. It's linear, right? Separating hyperplane because it's linear in Vx. But this function in the original space, because Vx can involve nonlinear transformations, for example, x2 squared, x1 squared. So if you go back to the original space, so this boundary become this boundary, okay, this boundary. And we know that in the separable situation, so this boundary is a safety boundary for -1. And this is a 0, right? And this is the safety boundary for +1. And this boundary will be translated to this boundary in the original space. And this boundary will be translated to this boundary in the original space. Okay, so that's a basic idea for we perform linear find linear classifier in this feature space, which can be translated to this nonlinear classifier in the original space. And here we actually know Vx, right? So originally we have x1, x2. Now Vx consists of x1, x1 squared, x2, x2 squared. So we know Vx, and then we can do this classification in the feature space. And we can add a lot of terms, say sine x2 or cosine x1 or x1, x2. We can add all those terms as our features. And supposedly we can do well if we add more and more features. And supposedly we can add infinitely many features. Okay, so that's the point of kernel. And in the kernel method, so eventually we realize that when we write our scoring function in the linear case, so this W hat is summation alpha I, yi, xi, right? And then the linear score is a W times x plus b. We plug in W hat here, we get summation alpha I, yi, and then this inner product plus b. Okay, so this is a learned classifier. Although in the linear case, you only need this, this formula to compute the linear score. But nonetheless, we can still write this in terms of the inner product. And in this form, this alpha I are computed by maximizing Q alpha. And the point is that according to what we have explained, Q alpha can also be written in this inner product form. Okay, although it's a little bit more complex because suppose you have 1,000 training examples. So here you need to add up this 1,000 inner product. And also here you need to add up this 1,000 times 1,000, 1 million inner product because you have xij, right? So in the training stage, if you write things in terms of inner product, you have a lot of inner product to add up. But in any case, you can see that all the computations can be done in terms of the inner product. Okay, so the training can be done in terms of this inner product so that you get Q alpha, and you can maximize Q alpha to get optimal alpha I. And then you plug in this alpha I here, you get your classifier for any future query example or testing example X. So this f of X is how you score a arbitrary X after you train a classifier, which means after you obtain this alpha I. Okay, and then you see that in order to kernelize this SVM by moving from the original space to this feature space, you only need to know the inner product, say phi xi. If you change x to phi x, then you change xi to phi xi, and this change to phi x. You only need to know the inner product of phi xi and phi x. And here, you change xi to phi xi, you change xj to phi xj. You only need to know the inner product of phi xi and phi xj. Okay, so therefore, it appears that for any two examples, either xi or x, or xi xj, or here we just write x and x prime. So if you change x to phi x and x prime to phi x prime, then the inner product change to from x prime to phi x prime, the inner product. And you can define this to be your kernel function k x prime for any two arbitrary x and x prime. And back to this one, this will be k of xi x. This will be the kernel of xi xj. Okay, so now the point is that you can make this k, the kernel function, to be explicit, but you don't even need to specify this feature vector explicitly. They can remain implicit, and it is an infinite dimensional vector. So as long as you know their inner product, then you can do all the calculations in training and in testing. Okay, so in training, you just replace this inner product by this kernel function xi xj, and then you can get your objective function, dual function. You can maximize this function to get your alpha. And then here, you only need to replace your inner product by this k kernel function of xi and x. And this way, you know how to score a arbitrary testing example. Okay, so that's the whole kernel trick. Unlike here, we know these features explicitly. Here, we don't even need to know the features explicitly. We only need to specify kernel. For example, this radial basis function, or the Gaussian function, as we specified in the previous lecture, measuring how close or how similar x and x prime is. And then you see that your classifier for a query x, for an arbitrary x, how you score this x, you just compare this x to those training examples. Suppose you have 1,000 training examples. You compare x to those 1,000 training examples, and then you sum over alpha I and k xi x and those yi. You interpolate those yi by alpha I. That is how influential this example is in determining this vector w, which actually means whether it is on the boundary, right? Because only those examples on the boundary have a say on determining this w, and then how close this xi is to this query x that we want to classify. Okay, and then in this testing case, if you have this x and you want to classify x, you only need to find those xi so that this function is substantially different from zero, about zero, which means you find the close friends of x so that this similarity function is bigger than zero. And then you let them vote. So yi can be positive or negative. And they vote based on how influential each friend is and how close each friend is to x. Okay, and then you let them vote. And then you add this b so that you get the score. And based on whether this score is positive or not, you classify this query x to be positive or negative. So that's the basic idea. So this is training and this is a learned classifier. And you can think of this as you interpolate those yi among those nearby examples. For example, if you have a positive example here, if you have query example here, you just interpolate the nearby examples. You see they are all positive. You classify them as a positive. If you have a query example here, you interpolate those examples, they are all negative, right? You classify them as negative. But on the boundary, you need to interpolate both the positive and negative neighbors or friends and let them vote. So that's the harder part. Okay, but in any case, you can see that here we have our classification boundary, which is actually our score is a w phi x plus b, right? So this is f of x. After you make the change, it become w. If you change this x to phi x, it will be w phi x plus b, right? And then it will change, and then it will be changed to this summation alpha I yi k xi x. So So therefore, if you look at this boundary is w phi x plus b equal to 0, right? And this and in particular, this is how we score this x. But the phi is actually phi is implicit. So this one is the same as this one. Okay, that is this function w phi x plus b is the same as the summation alpha I yi k xi x plus b, because if you change everything to as a feature, if you change this this xi to phi xi and change this x to phi x, okay, this is w hat phi x plus b, right? And then that will be summation alpha I yi phi xi times phi x, and phi xi times phi x is k xi x, so that the scoring function will be summation alpha I yi k xi x plus b. Okay, so that's the learned classifier. So that is you first find the logit score for this arbitrary x, and then you classify this based on whether f of x is positive or negative. Okay, so that's the kernelization trick. And I'm basically repeat what I talked about last time. And this certainly applies to the general situation, because in the general situation, you also want to optimize Q alpha. This Q alpha is still the same. And after you find your alpha, your classifier also remain the same. Okay, but what's the difference? The difference is that when you, let me see, I need to go this side. The difference is only in the dual optimization. So you maximize this Q alpha, but this time alpha I belong to 0 to C, the interval from 0 to C, because we show that alpha I is less than C from this part, okay, from here. So we introduce slackness variable so that by taking derivative with respect to psi I, we have alpha I equal to C minus mu I, and this is less than or equal to C. So this gives us a actual constraint. And then therefore the whole alpha vector is within a box, high dimensional box, 0 to C to the nth power, right? That's a n dimensional box. So this is called a box constraint. And because of the bias term, just like what we did last time, so we also have this constraint summation alpha I yi equal to 0. So we want to maximize this Q alpha, still the same Q alpha, but with this actual constraint, alpha I is less than or equal to C. So that's the actual thing caused by introducing slackness. And recall that if we assume B equal to 0, then we remove this one, right? We don't have this. This is caused by the derivative of Lagrangian with respect to B equal to 0. So we got this constraint. But if we don't have this B, so we assume B equal to 0, then we can remove this constraint so that we only need to maximize Q alpha for alpha I within this range. So this, we can again accomplish this by dual coordinate ascent. So that is, we go through I from 1 to n, and for in each iteration. And then for each I, we maximize this function as a function for alpha I, and we keep all the other alpha I fixed at their current values. Okay, so this is a coordinate ascent idea we discussed before. And if we allow B, then we have this one more constraint, summation alpha I yi equal to 0. And if we still use coordinate ascent, then each time if you update one alpha I, you are going to violate this constraint. So therefore, each time, at least you need to update two different alpha I and alpha j. So this is a slight extension for coordinate ascent. So instead of updating one coordinate, each time you update two coordinates. So this is called sequential minimum optimization, SMO. And in the linear case, actually, indeed, we want B, but in the kernel case, B is not that important. So in the kernel case, when we have Q alpha to be written as all those K, Xi, Xj, we probably can neglect B, and we can still learn a reasonable classifier. Okay, so that's a computational aspect. And then in terms of geometry, compared to what we did last time, we have this upper bound C. Remember that we last time for the separable situation, we interpret this max margin problem into a dual problem for minimum distance between two convex halls, right? So one is a convex shape, minimum convex shape, covering, including all the positive examples, and this convex shape, including all the negative examples. We want to find one point in this positive convex hall and one point in the negative convex hall, so they get minimum distance. And this minimum distance is actually the max margin, so that we can cut in the middle. So that's a separable case. And in the non-separable case, we have this upper I is upper bounded by C. Remember that this constraint actually tells us the alpha I for the positive examples, the summation of alpha I for the positive examples is the same as summation of alpha I for the negative examples. And we assume the sum equal to S, which is a positive number. And then we have this each alpha I, we divide each alpha I by S, so that we get this coefficient Ci and summation Ci are all bigger than or equal to 0, and they sum to 1 for both positive and negative examples. That's how we define the convex hall. With this upper bound, then each of Ci is less than or equal to C divided by this S. This C is a capital C divided by this S, which is a summation of alpha I for positive or negative examples. And then we only look at the interior. So with this upper bound for the Ci, and then summation of Ci xi for the positive examples only covers the interior of this convex hall of positive examples, similar for the negative examples. So therefore, we find the minimum distance between the interiors for the positive convex hall and the negative convex hall. Okay, and then we cut in the middle. So we still have this minimum distance interpretation for the dual problem. But this time, instead of finding the minimum distance between the two convex halls, we actually find minimum distance between the interiors of the two convex halls. So that's the key idea. So therefore, the primal problem is max margin geometrically, and the dual problem is mean distance. So we still have this geometric interpretation. Okay, so now let's look at the next page. So now we switch gear. We try to gain some understanding from the statistical perspective. In particular, we hope to connect this non-separable case to a familiar example, logistic regression. So we want to come back to logistic regression. Remember that when we start SVM, we start from a warm-up on logistic regression, and now we want to come back to logistic regression based on another way to translate the constraint. Remember that for this slackness, so if this yi times the linear score in the linear case is bigger than or equal to 1, so that means it is perfectly safely behind this safety boundary, right? And then we don't need to pay any penalty, or we don't need to buy any slackness. So psi I just equal to 0. But if this number is less than 1, so it go beyond the safety boundary. For example, if this number is 0.8, so it go beyond safety boundary. So this is 1, it goes here. And then you want to buy some slackness. But what's the minimum amount of money you can pay for the slackness? So if this number is 0.8, and you only need to pay 0.2, so that is optimal. The smallest psi I hat is just 1 minus this number. You don't want to pay extra, right? Suppose you buy a space for 0.2, or if you are 0.8, so you only need a space for extra space for 0.2. Then you don't want to pay the money like a 0.3. You don't need this extra space, right? So if this 0.8 is here, you just pay this 0.2. So the optimal psi I is simply 1 minus yi and this linear score. So therefore, if we combine these two to decide how much money we want to pay for the slackness, so we can write this as a max, but this is not a maximum over a continuous variable. It's just a maximum between two numbers. Okay, so 0 and 1 minus this number. So we call this linear score as SI. This is a logistic score, right, in the linear logistic regression. So if yi SI is less than 1, then 1 minus yi SI is bigger than 0, right? So that's the price you need to pay. Say yi SI equals 0.7, this is 0.3, and then you need to pay 0.3. But if yi SI is bigger than 1, 1 minus yi SI is less than 0, then the maximum between the two will be 0, so you don't need to pay. So that is, if you look at the yi SI, if it's bigger than 1, you are safe. You are behind the safety boundary, so you don't need to pay. But if you are here, say this is you are here 0.7, then you need to pay 0.3. And if you are here even negative, say this negative 0.5, then you need to pay 1.5. So that is here, if it's beyond 1, it is 0. But if it's less than 1, it will be 1 minus this yi. Excuse me. So this is a Hinge loss, because this is like a Hinge function, right? Hinge function, two-piece function. Okay, and then you see that our minimization problem becomes here. So we want to minimize 1/2 of L2 norm of W plus C, and then the optimal psi I, summation of optimal psi I, which is a max of 0, 1 minus yi SI, which is WXI plus B. So we need to solve this problem. We need to minimize this problem. This is another way of translating the primal problem. In the separable case, it actually corresponds to the situation where C is infinity. But otherwise, C is a positive constant in the non-separable case. And now we can connect this to logistic regression. So again, we have SI to be the linear score, WXI plus B. In logistic regression, we define PI to be sigmoid of SI, ESI divided by 1 plus ESI, which is the probability yi equals positive 1 given SI. So that 1 minus PI will be 1 minus this guy, which is 1 over 1 plus ESI, which is the probability yi equals negative 1 given SI. Here, I want to again make a note that in logistic regression, we often use yi to be 0 or 1, right? But here yi is not. We should have a not here. Yi is not 0, 1. Yi is positive 1 or negative 1. Okay, so this is another notation for yi. And for logistic regression, we can derive it in a different way because we use positive 1 or negative 1 notation. The point is that now we have this probability yi equal to positive 1, which is here. And then this is a probability of yi equal to -1, which is here. And you can actually combine these two things, because this pi, if you divide both the numerator and denominator by ESI, so you have 1 here, right? And then 1 plus E of negative SI. And then you can combine this with this one, so that this probability yi given SI is 1 over 1 plus E negative yi SI. Okay, so that actually covers this formula and this formula. Okay, but this is the expression for the case where yi is positive 1 or negative 1. Okay, it is not the case for yi equal to 0 or 1. For y equal to 0 or 1, we have different formula. Again, for this formula where we combine both positive 1 or negative 1 into a single formula. But this is a formula for the positive 1, negative 1 notation for yi. And then the loss function can be defined as the log likelihood. So the log of probability, and then we put negative sign, because we want to maximize the probability so that we have a good score to predict yi. And then we want to maximize the log of the probability or the log likelihood. And then if we put a negative sign in front, it becomes loss function that we want to minimize. Okay, and here, if you look at the negative log of this probability, so it becomes log for the denominator 1 plus e negative yi SI. So interestingly, this is also a function of yi SI. And if yi SI, this margin, the individual margin, goes to negative infinity, then this number become very big, right? This number dominate. So we can just discard this one, which is too small, negligible, so that we have log of this e, which will be negative yi SI. And if yi SI go to positive infinity, then this number go to 0. And then log 1 plus a small number, according to the Taylor expansion, you can do a Taylor expansion around 1. It will be just this small number. That is log 1 plus delta, a delta is small number, equal to delta. So this will be e of negative yi SI, we just copy here. Okay, so therefore, if you look at the negative side, on this side, so this is a hinge loss, and then this will be the this logistic loss. Okay, and this logistic loss on this side, on the negative side, it is something like here, negative yi SI, and this is similar to 1 minus yi SI in the hinge loss. Okay, on the left side. And on the right side, it is exponential negative yi SI. This is exponential loss. And this is actually the loss function for eta boost. So therefore, you can think of that in general, this SVM, the hinge loss function is a very crisp two-piece linear approximation to the logistic loss function. And this logistic loss function actually is similar to the hinge loss on the left-hand side, on this side. But on this side, it is smoother, right? Instead of setting the loss to 0 as a hinge loss beyond 1, it actually goes to 0 at the exponential rate. Okay, and also it agrees with exponential loss on the positive side, but on the negative side, the exponential loss penalize this negative YSI much more severely than the logistic loss, because usually eta boost works very well for the so-called separable case, but for the non-separable case, it penalizes misclassification where YISI is less than 0 more severely than SVM or logistic loss. Okay, so therefore now this plot actually shows the connection we may somehow claim that the ADA boost using the the exponential loss is a approximation to logistic regression. And SVM with its hinge loss is also a approximation or modification of logistic regression. Although this hinge loss is rather foreign to statisticians, and this cannot be interpreted as a log of probability. It is only a approximation, but also this hinge loss, as we showed before, lead us to this support vector type of treatment and this primordial treatment. This is also highly unusual to a statistician. But still, by writing this primal problem in the form of hinge loss, we were able to connect the SVM to logistic regression. So we can rewrite this SVM as the summation of the hinge loss plus 1 over 2c and L2 norm of W, or the squared length of W. This is the same as the previous one. The previous one, we have 1/2 of W plus C times this one, right? We just divide the whole thing by C. So we get summation of this one plus 1 over 2C times this L2 norm of W. And for logistic regression, where yi is positive 1 or negative 1, so our loss is summation of logistic loss, log of 1 plus exponential. There should be a yi here. There's a typo. There should be a yi here, and then the linear score. And if we also add lambda, we penalize this W. We never penalize the intercept. We penalize the squared norm of W, the L2 norm, sum of squares of the components of W. Then this is very much like a ridge regression. And you can think of what we are doing here is a ridge version of logistic regression with this regularization. And therefore, you see a similarity. That is, here we have logistic loss, and here we have a hinge loss, which is approximation to logistic loss. And then we have the same regularization term, right? So L2 regularization or the ridge regression. So therefore, you can connect SVM to the ridge logistic regression. Of course, in ridge regression, this L2 norm of W comes from this shrinkage consideration. So it leads to a shrinkage estimator as a matter of regularization to avoid absorbing the noise, right? But in SVM, this comes from this margin consideration. But these two seem to be consistent, and the regularization point of view seem to be more general, although it is also more boring, right? We have been thinking about regularization, L2 regularization, or L1 regularization for many different cases. But still, this seems to be a reasonable connection or even a reasonable consideration of SVM. That is, even without this margin consideration. So by thinking of this as a matter of regularization, you still can explain why SVM works, doesn't overfit. And in terms of ADA boost, so ADA boost uses exponential loss, as I mentioned. And also in ADA boost, we keep adding the trees, right? So this is almost like adding new features. And this is actually consistent with lasso. Remember that when we perform this lasso coordinate descent type of computation, so this lambda of this L1 norm, this lambda plays a role of threshold. We do soft thresholding. And if we start from big lambda, then all those variables are 0, right? All those coefficients are 0. And if we gradually reduce lambda, then more and more variables will be included or selected. In that sense, the boosting or ADA boost, which perform forward selection, is quite consistent with this lasso philosophy. So that again, you use forward selection to gradually include more and more variables. But in AdaBoost, you keep adding the trees one by one. So that's on the L1 regularization side. L1 regularization gives you the selection, including forward selection. And the L2 regularization gives you the shrinkage, or also which can also be justified from this margin consideration. Yeah, I think this is the connection. So in this class, I always hope to show you the connections between different methods. And in particular, for classification, I always want to connect things to logistic regression. And today, as we show here, we can think of AdaBoost or SVM, the two powerful classification machines, as modifications for logistic regression. And in the next lecture, I will further show you that the neural network can also be considered as a generalization of logistic regression. In fact, it can be viewed as a logistic regression on top of logistic regression. So therefore, our knowledge about those important classifiers can all be traced back to logistic regression, which as a unifying point of view. I think we can stop here, and thank you for your attention.